onward with this talk about inertia and its relationship to mass. The amount of inertia possessed by an object, remember inertia is this tendency of things that are moving to keep moving and things that are sitting still to keep still. So the amount of inertia possessed by an object depends on the amount of matter, which is the amount of material that composes it, makes it up, which we call its mass. Now, we often think of mass and weight being the same thing, and we'll talk about in a little bit how they're not actually the same thing. But for this slide, you can consider mass and weight to be the same idea. So the trend goes, if we have a greater mass, we're going to have a greater amount of inertia. If we have a smaller mass, we're going to have a smaller amount of inertia. So if you were having to push one of these vehicles, a little Volkswagen Bug or a train engine, which one do you think would be easier to push and get moving? And you're probably right away saying, of course, the VW Bug is going to be easier because it's smaller. And likewise, if you were to, God forbid, get in a car accident with one of these, would it be less dangerous to be in a car accident with a Volkswagen Beetle or to get hit by a train? And of course, it would be more damaging to be hit by a train. The reason is the train has much more mass, not only the mass of the engine itself, but all the cars behind it, and therefore it has a much greater inertia. And we'll talk about in coming days why that bigger amount of inertia would be more damaging in a car accident. But what it means here, the train's heavier, so it's going to keep on moving a lot more easy. It's going to be a lot harder to stop. The Volkswagen Bug is lighter in weight, it has less mass, and therefore when it's at rest, it's easier to get it moving. So mass is a quantity of matter in an object. Now everything in the universe is one of two things. It's either matter or it's energy. Matter is stuff, like it's made from atoms. So think of yourself, your pencil, your phone, your computer, a cloud in the sky, the sun, the air that you're breathing, that's all matter. Energy is everything that's not matter. So think of things like light and like sound and heat. Those would all be examples of energy. So mass is a quantity of matter in an object, essentially how many atoms are in it. Mass is a measure of inertia or sluggishness that an object exhibits in response to any effort made to start it, or stop it, or to change its state of motion in any way. So as mass increases, inertia increases. Weight, on the other hand, is the amount of gravitational pull on an object. It's proportional to mass, but it's not exactly the same thing. If we have twice the mass, we're going to have twice the weight. If we reduce the mass in half, we're going to reduce the weight in half. The difference is, on the previous slide, mass is going to be the same if you're standing here in Heston, Kansas, or if you're on Mount Everest, or if you're standing on the moon, or you're in a spacecraft and you're flying past Jupiter. Your mass is always going to be the same. You're still made out of the same number of atoms, the same quantity of matter. Weight, on the other hand, changes as gravitational pull changes. So on Earth, your weight is going to be pretty much the same regardless of where you are. But think about if you're on the moon. You've seen pictures of astronauts on the moon, and there's gravity there, but they kind of bounce a little bit when they talk. There's less gravity. Because there's less gravity, their weight will be less. Meanwhile, if you were on Jupiter, which you couldn't be for a number of reasons, but say you could be on Jupiter and still be alive, Jupiter's gravitational field is many times that of the Earth, and so your weight would be much, much heavier if you were on Jupiter. More terms that we'll encounter. So we know mass, and comparing that to volume. So mass again involves how much matter an object contains. The volume involves how much space an object occupies. So mass, think of barbells. Volume, think of a measuring cup or a tablespoon or a gallon jug or something like that. The kilogram is the standard unit of measurement for mass around the world. Here in the United States, we're pretty much the only country, the only people in the world who don't use the metric system. We don't use the kilogram as our standard unit of mass. So I know I have some international students in class. This will be easy for you. For those of you who grew up in the United States, you might have to learn a little bit. So the kilogram, the standard unit of measurement. On Earth's surface, 1 kilogram of material weighs 10 newtons. If we put that into pounds, which people from the United States are more familiar with, that's about 2.2 pounds. 1 kilogram is about 2.2 pounds. 1 kilogram, like we see in this kilo bar of gold, is equal to 1,000 grams. And we'll use the metric system a little bit too, so we'll get to know what some of these prefixes like kilo and milli and deci and so on mean. The kilogram away from Earth, such as if you're on the moon, this kilogram bar of gold would still have a mass of 1 kilogram on the moon, but its weight would be less than 10 newtons or 2.2 pounds. Because remember, mass is the same no matter where you are. The weight of an object measured in newtons or pounds will change depending on how much gravity you're experiencing in that place. When the string is pulled down slowly, looks like I made a mistake with my picture here. Anyway, it says when the string is pulled down slowly, the top string breaks, which best illustrates which of the following. So in this picture, the hand is pulling down slowly, and the string that's between the hook and the heavy metal ball is the one that breaks. Which of these would explain that? So take a guess, think about it for a second, and then I'll show you. Okay, this string breaking demonstrates the weight of the ball. The explanation being the tension in the top string is the pulling tension from your hand plus the weight of the ball, both of which break the top string. In other words, the string between the hook and the ball is the one that feels the most tension versus the ones between the hand and the ball. On the other hand, when the string is pulled down quickly, if that hand snaps it down really quick, the bottom string breaks. What would that illustrate? That one illustrates the mass of the ball. So the string between the hand and the ball breaks when you snap it down quickly because it is the laziness of the ball that keeps it at rest, resulting from the breaking of the bottom string. Here I replaced the word inertia with laziness. Laziness, it doesn't want to move. That ball is heavy, it doesn't want to move because it has more inertia. So a quick snap breaks the string. When you guys all come back to class in person, I'll show you this. It's kind of hard to show over a PowerPoint though. So continuing on with the talk of mass, we talk about the measure of compactness. Density is the measure of how much mass occupies a given space. The equation for it is density equals mass divided by volume. The units would be grams per cubic centimeter, kilograms per cubic meter, grams per milliliter, something where you have a unit of mass on the top and a unit of volume on the bottom. In kind of normal people terms, density explains why you can have two objects. So imagine you have a cotton ball in one hand and you have a chunk of iron the same size as the cotton ball in your other hand. Which hand is going to be heavier? And you guys know the chunk of iron is going to be heavier, it's going to have a higher mass than the cotton ball. And the reason is the chunk of iron is more dense. There's more mass in the same amount of volume. That means its density is higher. And onward to some more terms. I mentioned the word force earlier. A force is a fancy sounding science word that really just means a push or a pull. There's nothing more to it, a push or a pull. The net force is a combination of all the forces that act on an object. So act on an object, that means if you have one object pulling and another one pushing, what's the average of that? A net force changes an object's motion. Okay, on the table at the bottom, we see two columns. We see applied forces and net forces. On the left side, on the top box, the applied force says we have two people pulling with 5 newtons of force, and they're pulling to the right. In the net force top box, we see a arrow. The pink arrow is twice as long as the pink arrows on the left, and it says 10 newtons. So what that means, if you have two people pulling with 5 newtons of force, their overall, net means overall, their overall force is going to be 10 newtons. You simply add 5 plus 5 and you get 10. In the second row down, we have a box. There's a person, they're pretty much playing tug of war. On the right side, person pulling to the right 5 newtons, on the left side pulling to the left 5 newtons. Overall, I mean, if you were playing tug of war with this, nobody would be moving because the net forces cancel out. 5 newtons left, 5 newtons right, cancel out to be 0 newtons overall. And on the bottom, pulling right with 10 newtons, pulling left with 5 newtons. If this was tug of war, which way would you move? The person on the right is pulling twice as hard, so you're going to move to the right. So the net force on the bottom one is 5 newtons. We get that from the 10 newtons minus the 5 newtons. So here's a picture of tug of war, if you weren't aware of what it is. I find international students or people from maybe different regions of the country don't always know what I mean by the words tug of war, but when I show the picture, usually people know what this is. So take a moment to think about this. Where are the forces? And in what direction are they going? Do you have an idea of in which direction the forces might be the highest? Okay, so we see looks like 4 kids on the right side. They are pulling, so their forces would be pulling to the right. We have, looks like 4 kids on the left side. They're also applying force to the rope, and it's in the direction of the left. So the net force in this is pretty hard to tell from a photo because we can't see the movement of which way they're actually going. There's probably also some force applied to the grass. I see some kids digging their feet into the lawn, so there's forces being applied to the grass below. Probably in several other examples also, but those are the forces that people normally notice. And that will wrap up our talk about Galileo, about Newton, mass, inertia, and forces for the day. So make sure that you've answered the questions on Top Hat, and we will continue with the second half of this chapter on the next class day.